Hey everyone, welcome to the last video for section 3.2. So in this video, I've got one more point to make about solutions to equations, and then we want to do two examples, one where we talk about finding a fundamental set and finding the special fundamental set discussed in the theorem in the book, and then we'll talk about interval resistance stuff like we did for first order equations. So let's go ahead and jump right on into it. So the last point I need to make about equations is complex valued solutions. So there will be times in this course where we're going to have to deal with complex valued solutions. I'm going to have videos on the complex numbers too if you want some more information about that. But the idea is if I have a function L, or an operator L, sorry, so L of y equals 0, my normal differential operator that's linear, then if I have a complex valued solution of that, I actually get two real valued solutions from that. So if I have L of y equals 0, where y of t can be written as u of t plus I v of t, where I is the imaginary number I, square root of minus 1. And I know that my functions p of t and q of t are real valued, so they don't involve complex numbers. Then what do I get out of this? Then the result is L of u is 0 and L of v is 0. And these are both real valued functions because they're the real and imaginary parts of my complex valued function y. So if I have solutions that are complex valued and all of my coefficients are real, then I get two solutions from that. I get the real part and I get the imaginary part of two separate solutions. And this is the content of theorem 3.2.6. You can look in the book if you want to see the proof of how that theorem is actually proved, and I'm not going to stress it too much right now. But when we get into section 3.3, we're talking about complex roots of the quadratic equations. This is going to be very important to know this and to see where it's coming from. Because in the future, if you have a physical situation that is in modeling something, your solution should not be complex valued. Why? Because if I'm talking about a mass on a spring, complex numbers don't make any sense. If I say it's 3 I units away from the center, that means nothing. It's a nonsensical statement. So answers that would be complex should not end up being complex, and you're going to want to take the real and imaginary parts instead as your functions. So that's the main point here to mention now, and I'll hit it again in section 3.3 when we talk about complex roots to the characteristic equation. So let's go ahead and jump into our examples for this video. Example 1, I guess part A. Find a fundamental set of solutions to y double prime plus 3y prime plus 2y equals 0. So how do we find solutions? Well, first, let's find two solutions and then make sure they're a fundamental set. So my characteristic equation is going to be r squared plus 3r plus 2 equals 0. And this factors r plus 1, r plus 2 equals 0. So my general solution, or at least what I claimed before was a general solution, is y of t equals c1 e to the minus t plus c2 e to the minus 2t. So my y1 is e to the minus t, and my y2 is e to the minus 2t. So let's verify that these guys are in fact a fundamental set of solutions. So let's check their Wronskian. So the Wronskian is going to be y1 of t. I'm going to leave it as the function of t here, and then we'll check it later. y2 prime of t minus y2 of t, y1 prime of t. So we plug in. This here is e to the minus t. This is minus 2 e to the minus 2t minus e to the minus 2t minus e to the minus t. Multiplying through, this gives me a minus 2 e to the minus 3t plus an e to the minus 3t, which gives me a minus e to the minus 3t. And what do we know about this function? This function is never 0, ever. So what that says is these guys are a fundamental set of solutions. Fantastic. So So y1 of t equals e to the minus t, and y2 of t equals e to the minus 2t are a fundamental set of solutions. Cool. Now part B, find the set of fundamental solutions corresponding to, I'm going to use different letters here to denote different things. W1 of 0 equals 1, W1 prime of 0 equals 0, W2 of 0 equals 0, and W2 prime of 0 equals 1. So this is from the theorem we use to say that fundamental sets of solutions always exist. Now we know, because we found a fundamental set of solutions, is that these guys must be linear combinations of them. So I know W1 is going to be C1y1 plus C2y2, which is C1 e to the minus t plus C2 e to the minus 2t. And the same for W2. W2 is going to be D1y1 plus D2y2 is going to be D1 e to the minus t plus D2 e to the minus 2t. So now I just got to find my C's and D's based on my boundary conditions, or my initial conditions above. So let's start with the C's. W1 of 0 is C1 plus C2, and I want this to be 1. And W1 prime of 0, we did this calculation earlier, is minus C1 minus 2C2, and I want that to be 0. So I add these together. I get that I want 1 equals negative C2, so C2 is minus 1. And then since I need them to add to 1, this gives me C1 equals 2, because 2 plus minus 1 is 1. And now let's solve for the D's. I get the same system of equations, just with 0 and 1 on the left instead of 1 and 0. So 0 equals D1 plus D2. 1 equals negative D1 minus 2D2. Again, I get 1 equals minus D2. D2 is minus 1, and then D1 equals 1 from the first equation again. So, putting all of this together, let me leave it right there. Good. I get my W1 of t is going to be 2 e to the minus t minus e to the minus 2t. And my W2 of t is going to be e to the minus t minus e to the minus 2t. Because I just plugged in C1 and C2, D1 and D2 for their places above, right in this equation right here. So this gives me a fundamental set of solutions that is, the first one is 1 at 0 and its derivative is 0. The second one is 0 at 0 and its derivative is 1. This is the special fundamental set of solutions that are described by the theorem in the book. All right, so there's our first example. For our second one, it's going to be a quick one about interval of existence. So example 2 is going to be find the largest guaranteed interval of existence for the solution to t minus 5 y double prime plus y prime plus log of t times y equals 0, with y of 1 equals 3 and y prime of 1 equals 2. Now this problem is pretty simple. This is very close to what we were doing, very similar to what we were doing in section 2.4 about the first order equations. So the first thing we have to do is put it in standard form, which means I have to get rid of the coefficient of y double prime. So I get y double prime plus 1 over t minus 5 y prime plus log t over t minus 5 y equals 0. And now where are my functions p and q discontinuous? Well, these guys are discontinuous at t equals 0 for the log term and t equals 5 for the denominators. So if I'm starting my solution at t equals 1, how long can it exist? It must exist between 0 and 5. Because it's linear, I get all the way to 0 and all the way to 5, and I know I'm in that middle part because I start at t equals 1. All right, that is the answer for this one, is just 0, 5. All right, that's it for this video. For the examples of stuff using these theorems, there's going to be no problem in this one. So the next thing we're going to do is we're going to look at section 5.4 briefly, which is another second order equation. It's not constant coefficient, but we have another easy way of finding a solution. So we'll look at that real quick for tomorrow. And then starting next week, we'll go back and look at sections 3.3 and 3.4, where we're talking about what happens if the roots aren't real and distinct. What are the other two options, and learning how to solve those constant coefficient equations. All right, thanks a lot for watching, and then I'll see you in the next one.